Assalamualaikum and good day to all my panels. My name is Tuan Norliza Hanim Binti Tuan Hussin. My metric number is B0519100034 and my project ID is 118. My supervisor is Associate Professor Dr. Amri bin Sulaiman. So today I would like to present my final year project 2, which is entitled Investigations on the surface roughness value of the Nimonic C-263 Alloy during turning under multi-coolants. So today I would like to present on introduction, problem statement, objective, literature review, methodology, results and discussion, conclusion and lastly recommendation. As for the introduction, in this study, I used Nimonic C-263 Alloy. As we all know, a Nimonic C-263 Alloy consists of alloy that acknowledge the dominant machine-like ductility and creep strength at high temperature, high fatigue strength, and frequently superior corrosion and oxidation resistant at elevated temperatures. According to Sun et al. 2018, Nimonic C-263 Alloy have high temperature properties, which expose cutting tools to extreme heat, pressure, and abrasion, causing a rapid flank wear, crater wear, and tools notching at the tool's nose, as well as making them extremely difficult to machine. Due to its outstanding performance, this material is widely employed in heavy industry like aerospace, power generators, turbine blade, as well as heat exchangers. Apart from that, for this experiment, this Nimonic C-263 Alloy has been undergone a tuning process using PVD coated carbide in two machining conditions, which are dry and flooded condition. Jahanur Rahman et al. 2020 regards that flat coolants improve the quality of the machine surface and machining precision by ensuring good cooling effects and smoother machining performance. Flat coolant also mostly utilized in industry as cutting flat to lubricate and cool down the machining process. As for the dry machining, it offers a variety of benefits including more flexibility, increased productivity, shorter cycle times, and lower machine tools cost. It also does not pollute the atmosphere or water, lowering the risk of illness, skin irritation, and respiratory system. As for the problem statement, is the problem that we have counted for this scenario is the heat concentration at the cutting tool results in significant surface degradation. High temperature properties of the material itself affect the dimensional accuracy and surface integrity. Cutting flats are known to be harmful to machinist health and can occasionally slow down production. And lastly, dry machining can be an excellent alternative, but the lack of cutting oil causes excessive friction and heating during the machining process. The objective of this research is to determine the significant factors onto surface roughness for both condition, dry and flat, through ANOVA analysis. Secondly, is to investigate the surface roughness values of Nimonic C-263 Alloy under flat and dry condition. So let's proceed to the literature review. This is the summary of past research analysis. Based on the slide, I have been wrapped up a few authors that have been studied on the same scope of my research, whereby the cutting parameters that I use is still on the range of their study, which I can refer with. As for the methodology, this is the flowchart of my research. There are three levels of three cutting parameters that have been selected for this study, which are cutting speed, which is 60, 90, and 120 meter per minute, feed rate 0.05, 0.10, 0.15 millimeter per revolution, and depth of cut is 0.3, 0.4, and 0.5 millimeter. As for the experimental equipments for this study, the turning of Nimonic C-263 Alloy, which comes in size 90 x 150 mm, is done by using a CNC lathe machine using PVD coated carbide insert. Moreover, a portable surface roughness tester, Me22USJ310, is used to measure the surface roughness of the machine surface. The picture attached also shows how the workpiece setup and portable surface roughness tester was set up during the measuring process. The portable surface roughness needs to undergo calibration of the profilometer using standard GIS 1994 before measuring the machine surface. This portable surface roughness tester has a huge LED panel which allows easy reading of the roughness value and automatically generates the graph for the surface roughness via the fast thermal profile speed printer, which is able to print out the result faster and clearly. For the surface roughness value results, in this study, I take 5 times and then I calculate the average of the surface roughness value. Next are the results and discussion. As we all know, in terms of surface roughness, we're definitely looking forward to the smallest value, which is the term the smaller the better. As we can see on the slide, the table shows the result of surface roughness value in flat condition. The best surface roughness value for flat condition occurs at 0.2563 micrometer at 90 meter per minute of cutting speed, 0.05 millimeter revolutions of feed rate, and 0.5 millimeter depth of cut. For the highest RA value for flat is 1.309 micrometer at 120 of cutting speed, 0.15 of feed rate, and 0.4 depth of cut. Besides, as for the dry condition, the best value of surface roughness is 0.414 micrometer, which is happened at 90 meter per minute cutting speed, 0.05 millimeter revolution per feed rate, and 0.3 depth of cut. Meanwhile, for the highest value of surface roughness for dry machining is 1.1969 micrometer at the cutting parameter of 90 of cutting speed, 0.15 feed rate, and 0.5 depth of cut. Graph average of the surface roughness for both conditions also attached together on the slide. To achieve the objective of this study, here is the comparison results of surface roughness for both mentioning conditions. As we can see on the slide, the value of surface roughness for both conditions are comparable. Although not all values of surface roughness in flat mentioning are lower than in dry, but most of the flat mentioning resulted in better surface roughness value rather than in dry mentioning. Despite of that, the result of RA for both conditions have also been compared between various cutting parameters. As we can see, the first bar graph shows the surface roughness value at constant cutting speed, which is 120 meter per minute, depth of cut 0.4 mm, and various feed rates. The graph shows that when the feed rate is increased, the surface roughness value also increased and also been supported by acceleration at all 2011. The second graph shows the surface roughness value at a constant feed rate, which is 0.05 mm per revolution, depth of cut 0.4 mm, and various cutting speed. The surface roughness value is gradually decreased in both conditions when the cutting speed is rising. The third graph shows the surface roughness value at constant cutting speed, which is 120 meter per minute, feed rate 0.1 mm per revolution, and various depth of cut. The surface roughness value for both conditions are not consistent based on past research. Some researchers, however, argue that the depth of cut factors has a negligible effect on surface roughness until 2011. This slide shows the ANOVA analysis for surface roughness in flat condition. The table indicated that the p-value is 0.0001, which is much lower than the significant value, which is 0.05. P-value less than 0.05 indicates that model terms are significant. Obtaining from this analysis, it shown that cutting speed and feed rate model are significant. The resulting ANOVA table obtained the value of f-value for feed rate, which is 113.01, which is higher than f-value for cutting speed, which is 10.85, and the depth of cut 3.06. This result obtained that the feed rate is the most significant factor in determining the surface roughness value compared to the cutting speed. As for the dry condition, the ANOVA analysis result is depicted on the slide. Obtaining from this analysis, it shown that feed rate and depth of cut model are significant as the p-value for both model is below 0.05. Similar in flat condition, feed rate also be the most significant factor in dry condition as it results in the highest f-value, which is 114.84 compared to depth of cut, which is 18.87. What I can conclude from this ANOVA analysis is feed rate model is the most significant factor that affecting the surface roughness value. Apart from that, the effect of mentioning parameter also be compared for both mentioning condition. As we can see for cutting speed factor, the gradient line of surface roughness versus cutting speed is small for both conditions, which means that cutting speed factor for both conditions is not the most significant factor. Differ for the feed rate factor, as illustrated in figure 2 and 5, the gradient line of surface roughness versus feed rate is large. Therefore, the feed rate factor becomes the most significant factor towards surface roughness for both conditions. Lastly, the gradient line for depth of cut can be classified as horizontal, where both conditions show different behavior. The comparison of surface roughness has been investigated in this research. There are some conclusions can be reached based on the research finding for both conditions. To conclude this study, the objective that has been stated need to be achieved. For first objective is to determine the significant factors onto surface roughness for both conditions, dry and flat, through ANOVA analysis. The most significant factor in surface roughness for flat condition was feed rate, followed by the cutting speed and the depth of cut. And the most significant factor that affected the surface roughness of Nimonic C-263 Alloy in the dry condition was the feed rate, followed by the depth of cut and the cutting speed. This result observed that the most significant factor that affecting the surface roughness in both conditions was the feed rate. Second objective is to investigate the surface roughness value of Nimonic C-263 Alloy under flat and dry condition. Result obtained shows that the highest value of surface roughness in flat coolant is 1.309 micrometer and the best surface roughness value is 0.2563 micrometer. Meanwhile, for the dry condition, the highest value of surface roughness is 1.199 micrometer and the smallest value of surface roughness is 0.414 micrometer. The cutting parameter that influence the surface roughness value for both conditions would be varied as stated on the result table as depicted in the result. Lastly, in this slide also attached the mathematical model for surface roughness in both conditions, which generate from the ANOVA analysis. Term A is consists of cutting speed, term B is feed rate, and term C is depth of cut. The recommendation that I can suggest from this study is to compare the surface roughness value in other mentioned conditions like MQL and cryogenic in order to see which condition affect the surface quality the most. Next, maybe for the next study should be include further analysis on chip formation, surface microstructure and micro hardness as well. Then, to achieve good results in any experiment, the experimental equipment needs to be serviced and calibrated regularly to ensure that the equipment used are in a good condition. I think that's all for me. Thank you and Assalamualaikum.